Good afternoon, I'm Joanna Jordan, and as one of the organisers of this meeting, I'm delighted to chair this first session. Each speaker has a 20-minute slot, which includes a few minutes for questions, so please do post your questions in the chat during their talk, and then I'll pose them to the speaker following their presentation. So firstly, it's my pleasure to introduce Dr. Liora Malki-Epshtein from University College London, who will be talking about protecting the health of key workers with better air quality in vehicles inside and out. Thank you.
Thank you. I assume that IT will share my presentation now. And you can confirm that you can hear me?
Yes, we can hear you.
Thank you. So thank you for inviting me. I just wanted to talk about a number of COVID projects that I've been involved with over the past year, relating to transport vehicles and key workers such as bus drivers and municipal waste collection crew as well. I'll discuss the way that aerosol science actually filters into some very practical applications and case studies, and the role of ventilation systems and air quality, indoor air quality in those environments that needs to be looked at. I'll describe some, just briefly, some ongoing work that we're carrying out as part of Project Viral, but I will first start with the bus driver protection study that had was already resolved and that started in the spring of last year. So we were contacted by Transport for London in April of last year, the Department of Civil Engineering and the Center for Transport Studies at UCL to try to understand what mitigation measures we could offer and could we model them to protect bus drivers, because there have been a number of tragic deaths of bus drivers in London in particular. So we were first asked to look at the risk from droplets and at potential modification of the assault screens that already existed on London buses. Sadly, the buses already had assault screens fitted to them to protect against physical assault a number of years ago. And it was felt that there were a number of holes around these screens and speech holes, and that if those were sealed off, the drivers would be protected against droplets, which at that time were believed to be the primary source of infection along with surfaces. So we were asked to look at also advise on improving cleaning practices and to model the risk of droplets. What we agreed immediately was that simulating droplets was not enough. We were aware that there were a number of publications already out, like from Moravska, saying that aerosols need to be looked at as well, and that we were aware that those remain airborne for long periods of time because of their size. So we took the example of 2 micrometer aerosols that have a sink velocity of 10 to the -4. And it would take, in stagnant air, it would take aerosols of that size 4 hours to drop to the floor if they're released from the height of a person breathing out. So the first piece of work that was done was carried out by Professor Thorsten Stoser from our department and his research associate Alex Stubbs, using an in-house code for which they could carry out very high resolution large eddy simulations to understand the details of airflows and concentrations. And those were run thanks to the help from the Met Office, who stepped in to help run the simulations more quickly because the project was so urgent. The intention was really to provide very urgent advice as much as that's possible with CFD, and to simulate first the worst case spreading scenario, which was simply the scenario that existed at the time, with the existing assault screen and a passenger standing right in front of the assault screen, coughing 5 times and then breathing normally for about a minute. And aerosols were modeled only for the 2 micrometer size for practical reasons, obviously. They were simulated as passive tracers, and it was shown how they can disperse around the bus due to the internal airflows and how they might enter the cab of the driver. And a number of scenarios were simulated based on requests. Again, bearing in mind there was very little known at the time, requests to look at things like social distancing and enhanced protections for drivers around the assault screen. So I won't talk too much about the CFD simulation, but this was the domain. These were the just a sense of the geometry that was being modeled. These are CAD drawings, and we're looking at, on the left side, the pre-COVID cab with large gaps around the screen, particularly around the screen and in the speech holes, and the modified assault screen that had much minimized gaps between the saloon and the cab of maximum 5 millimeters. So we adopted, as I said, the precautionary principle of warning that aerosol transmission may be an issue as well. And therefore the models, the simulations of the very worst case scenario are shown on this slide. We have 3 selected horizontal planes. So at a height of 1 meter from the floor, that's graph A. At a height of 1.5 meters from the floor, graph B, and graph C is at the top. At 2 meters where there were gaps around the screen as well. These contours are on a logarithmic scale, which was selected simply so that the concentrations could be resolved and understood and visualized, and they're taken at 60 seconds. So as I mentioned, we had to look at a large number of simulations and case studies, looking at the pre-COVID case, at what would happen if speech holes would be sealed. That was the initial intervention that was already taken up immediately. Middle door boarding was tried for a while with the understanding that this might minimize droplets specifically because of creating a distance between passengers and the drivers. Therefore, we looked also at the case of physical distancing with the passenger standing 2 meters back. But of course, we then started to say that in fact the middle door boarding was not actually such a great idea because it trapped the aerosols closer to the driver's cab. So we started looking at cases where front door boarding was employed or both doors were open, and the case of opening the window for the driver in order to provide fresh air for the driver. So this led to really a very large number of case studies, and this is just an example of the results of those. The full results are in the report. These contours show only at the height of 1.5 meters, so at the height that the aerosols are exhaled and coughed out for the various scenarios, and they're laid out on the screen a bit differently. So just to look at front door boarding, what was the pre-pandemic case, the impact of sealing speech holes, and the impact of the modified screen, which is the one on the right, which is case number 6. Then showing you the impacts of middle door boarding, what happens with physical distancing, and is there any improvement if the passenger is standing 2 meters away, which there wasn't because of the airflows on the bus. What happens with middle door boarding with the impact of the modified screen that is almost entirely sealed off. And our final recommendations were to modify the assault screen to leave only minimal gaps around them and to open the window, which was the result of case 9, in which case no aerosols were entering the driver's cab at all. So of course, it became quickly clear that there was an infinite number of possible scenarios of airflows on the bus. And I started to ask, what is the exposure for the drivers? Is that some kind of common parameter that we could use to compare all the case studies to each other and to see really in a clear and concise way how this can be reduced with mitigation measures? So given that there wasn't enough quantitative science on virus load or infection risk, we only modeled exhaled breath. And this exposure is 60 seconds of breathing in exhaled breath of the passenger, where that exhaled breath can contain anything. And as we know, the likelihood of that containing a virus particle is actually extremely small. But over the course of a shift of 8 hours and a large number of passengers boarding, that becomes more of a concern. So we try to just list a whole set of interventions to take a very practical approach of comparing these exposures and seeing which of them would be the most, which intervention would be the most useful. By far the best intervention we found was the modification of the assault screens. It doesn't require any behavior changes. It doesn't require any assumptions about face masks. When we started the study, face masks were not recommended at all. They became implemented on the Transport for London network in June, following advice from Public Health England, but until then there were concerns about shortages of PPE, so those could not really be advised. And in any case, many people do not wear them. So the modification was the most precautionary mitigation that could be taken. Opening the window in the driver's cab was shown to be really highly effective. It was an immediate solution that could be implemented. It also helped to protect against driver fatigue and to prevent mold from growing in the driver's cab. And sealing the assault screen speech holes, of course, was recommended, but it was shown that on its own, it would not be effective enough. So we made a whole set of recommendations that were listed here. So modifications for the assault screens. And what was really important was to understand that there needs to be a complete avoidance of recirculation of the air between the saloon and the driver's cab. And that's the point where starting to look at standards for ventilation and air quality on vehicles started to concern us, because we couldn't really find very clear guidelines and standards in the same way that you would find in buildings. So we really took a very precautionary principle, separating everything, following advice from building ventilation guides, from SIBSI and from any other organization, and to request that windows would be open until the ventilation systems could be adapted. So in terms of results, TfL took on board our recommendations and retrofitted its buses. In terms of the assault screens, these kind of figures show how they were modified. I know the 5mm gap is questionable. That's really a very practical issue of implementation, having to retrofit these screens on buses that vibrate very heavily and are in motion and have already a windshield attached to them, meant that there had to be some gaps in terms of how these were fitted, but the simulations at least showed that those could still be made completely safe. After that, a few months after that, the project obviously continued. At that point, we started Project Viral already, and the recommendations we made in the first stage were then adapted so that all buses were adapted to avoid recirculating air, and to prepare for the winter, when our recommendations for opening the windows were not very welcome. 1,200 buses were fitted with a separate driver cabin ventilation system to enhance their protection and separate, to provide additional ventilation for them. So I'll just talk briefly about Project Viral. It's still ongoing, and there's not much that we can report yet, but the project is led by Lena Sirik at UCL, with several co-investigators from transport studies, environmental fluid mechanics, air quality, and several research associates. And we really aim to kind of connect the dots between microbiological surveys of air and of surfaces, air quality analysis and ventilation analysis, airflow simulations where appropriate for specific cases, and passenger crowding. So I think I've just mentioned this already. We have recommended that air quality targets be adopted on vehicles. In large cities, this is by no means restricted to London only. In any large global city, there will be a very high number of passengers every day. And on large cities like Paris or New York or Tokyo, you do often have commutes that are quite long. They might be over an hour long, maybe on several different transport systems, maybe jumping from bus to rail to tube to bus again. And there are really good reasons to improve air quality anyway. I think a year ago, we probably still needed to say, this may be a long-term problem with infectious diseases every year, like the flu, or the emergence of pandemics every decade or so around the world. I think we don't really need to make the case anymore on how important this is. We have been carrying out CO2 measurements on buses, doing long-term monitoring, as well as using our own bus owned by UCL, by Nick Tyler at Pamela Lab, in order to test things like ventilation flows and CO2 levels with passengers on buses. We have not finished the study and we can't share all the results yet, but the initial findings were enough to convince Transport for London that it would be really useful, practical, and that it would work if we introduce open windows on buses. So they've reported on this. They're leaving now customer messaging to leave the windows open, adding instruction stickers to all the windows on the fleet. And that in addition to the fact that numbers are restricted and face coverings are in use and the public are encouraged anyway to walk and cycle where they can, means that the situation is really much, much improved. But the work will still continue, especially in terms of commissioning for the future. I always get their emails, so I just wanted to say, as a passenger, you can always get their updates, and they describe quite nicely there the importance of face coverings and air circulation on trains and buses and how they fitted their ventilation systems. So that's been quite nice to know that the modeling of aerosols was so helpful in making the case for all of that needing to be done. Finally, I think I'm overrunning a bit. I'll just mention that we also carried out a study with Veolia to look at municipal waste collection crews. And we measured CO2. We did some long-term monitoring on some of their vehicles and found that they do need to be better ventilated again, and that if we want to be very cautious with crews that do have to work together and be on the same vehicle in a cab that allows for some social distancing, but still without fresh air, aerosols would still build up in the space. So we recommended, again, for now, opening the windows and then improving on vehicle design for the future. And those recommendations have been accepted as well. And this is where I mentioned in the title of my talk, indoor air quality and out, because there is a conflicting agenda, particularly in the vehicle industry. Standards of ventilation do not actually exist. The legislation isn't as strict as it is for all the other measures that the vehicle industry have to report to. And at the same time, there is a very strong push to reduce emissions and energy use. And all of that means saving fuel, and often that may possibly come at the expense of HVAC systems. On top of this, we have vehicles that are designed to be increasingly more better sealed so that they're less noisy and more comfortable inside. But all of that means that if you do not deliberately introduce fresh air into the space and the vehicle is shared by a number of people, you do run into the risk of airborne transmission becoming important. So it really is, I think, something that needs to be looked at quite a lot. And I've raised a few questions that I think are going to be discussed in the first discussion session. It would have been really nice to hear from the rail people as well today. So it's a shame they can't join us, but I believe this is a shared problem across many places in public transport. That's it for me. Thank you.
Many thanks, Liora. We've had our first question come in on the chat. If I read it out to you from Jorge Apont Gomez. Why not make a design of buses without windows, just an air duct? We have the same problem in Bogota with Transmilenio.
An air duct might be possible, but there are so many constraints in terms of vehicle design and the structural stability of the buses that actually rely on the windows for structural stability as well. So it wasn't really the most practical thing to do. But they have retrofitted ventilation systems based on whatever practical measures they could come up with. And that's far beyond my own expertise. We could only recommend that it be done.
Great, thank you. As we wait, we've still got a couple of minutes for any additional questions. I had one is, has your work been taken up outside of London?
I'm not sure, to be honest. We work quite closely with TfL, so we're more aware of any mitigations that they have carried out, but I would hope so.
I hope so too. It's great to hear more about your work.
I can't actually see the chat, so.
There's nothing there at the moment, but very fortunately, Liora has kindly agreed to chair one of our breakout discussion sessions later, so you'll have time to quiz her then.
Yes. I see there is a question from on a reduction of infections. That's a subject of an investigation by another group at UCL, the Institute of Health Equity. Their study was carried out up until January this year and has seen a reduction in infections. It hasn't been able to link the infection reduction to any specific mitigations, as it relied primarily on questionnaires with bus drivers. But in any case, whatever the reason, we're extremely happy that there's been a reduction in infections. And I think it's a joint effort that requires many different layers of public health and many different layers of protection. So I don't know if it would be possible to say that aerosol specifically made a difference because so many mitigations were taken up. But at least the mortality rate has dropped a lot, which is good.
Great, thank you. Sorry, I didn't see there were 2 chat boxes going on there. Thank you for fielding that. I'm afraid the 20 minutes is up, but there are more questions. As I said, I hope there'll be a chance to discuss them later on. So many thanks, Liora.
Thank you.